Welcome to Lasea class. I am your teacher, Jan Lasea. Today we are going to learn machine learning with naive-Bayes classification algorithm. Machine learning is the practice of programming computers to learn from data. It is a discipline of data science that applies statistical methods to improve performance based on previous experience or detect new patterns in massive amounts of data. Machine learning concentrates on prediction based on already known properties learned from the data. When should you use machine learning? When you have a problem that requires many long lists of rules to find the solution. In this case, machine learning techniques can simplify your code and improve performance. Very complex problems from which there is no solution with a traditional approach. Non-stable environments, machine learning software can adapt to new data. Types of systems of machine learning. Number 1. Supervised learning. The data that you fed into the algorithm with the desired solution are referred to as labels. Examples of supervised learning are key-near neighbors, linear regression, quadratic regression, polynomial regression, logistic regression, neural networks, support vector machines or SVM, decision trees, and random forests. Number 2. Unsupervised learning. The data is unlabeled. It means it finds the patterns, solutions, and clustering. Some examples of unsupervised learning are clustering such as k-means, hierarchical cluster analysis, association rule learning such as ECLAT, a priori, visualization and dimensionality reduction such as kernel, PCA, T-distributed, PCA. Number 3. Reinforcement learning. An agent, AI system, will observe the environment, perform given actions, and then receives rewards in return. With this type, the agent must learn by itself. You can find this type of learning type in many robotics applications that learn how to walk by itself. Number 4. Batch learning. The system cannot learn incrementally. The system must obtain all the needed data. That means it will require many resources and a huge amount of time. So it's always done offline. So to work with this type of learning, the first thing to do is train the system and then launch it without any learning. Steps in machine learning. Step number 1. Import the data. Assign the collected data as dataset and load into the machine learning software. Step number 2. Clean the data. Remove data redundancy or duplicate data. Step number 3. Split the data into training and test sets. Training dataset is about 80% and test dataset is about 20%. The TensorFlow with Keras need another type of dataset which is validation. If there is a validation dataset, therefore the training dataset is 80%. The test dataset is 10% and the validation dataset is 10%. Step number 4, create a model. Step number 5, train the model. Step number 6, make predictions. And finally, step number 7, evaluate and improve the model. Collecting data and training the model are the time-consuming parts of machine learning. Under the classification algorithms, we will learn the naive Bayes classification algorithm based from statistics and probability. Probability is the likelihood or chance that a particular event will occur. The probability of an event is the proportion of cases in which the event occurs. Probability can be expressed mathematically as a numerical index with a range between 0, an absolute impossibility, to 1, an absolute certainty. Most events have a probability index strictly between 0 and 1, which means that each event has at least two possible outcomes: favorable outcome or success, and unfavorable outcome or failure. Conditional probability. Let A be an event in the world and B another event. Suppose that events A and B are not mutually exclusive, meaning both events A and B can occur, but occur conditionally on the occurrence of the other. The probability that event A will occur if event B occurs is called the conditional probability. Conditional probability is denoted mathematically as the probability of A given B, in which the vertical bar represents given, and the complete expression is interpreted as a conditional probability of event A occurring given that event B has occurred. This formula is the Bayesian rule or the Bayes theorem. The probability of A given B is equal to the probability of B given A multiplied by the probability of A divided by the probability of B, where the probability of A given B is the conditional probability that event A occurs given that event B has occurred. The probability of B given A is the conditional probability of event B occurring given that event A has occurred. The probability of A is the probability of event A occurring without any conditions, also called prior or marginal probability. The probability of B is the probability of event B occurring without any conditions, also called prior or marginal probability. In statistics and probability theory, the Bayes theorem, also known as the Bayes rule, is a mathematical formula used to determine the conditional probability of events. Essentially, the Bayes theorem describes the probability of an event based on prior knowledge of the conditions that might be relevant to the event. The theorem is named after English statistician Thomas Bayes, who discovered the formula in 1763. It is considered the foundation of the special statistical inference approach called the Bayes inference. The formula that we learned previously is the Bayes theorem, which is this formula. The probability of A given B is equal to the probability of B given A multiplied by the probability of A divided by the probability of B. Naive Bayes is a classification technique based on Bayes theorem, with the assumption that all feature variables are independent. Thus, a naive Bayes classifier assumes that the presence of a particular feature in a class is unrelated to the presence of any other feature. The English word naive means it is very simple and inexperienced. To understand better the naive Bayes classifier, let us solve a classic problem. Given this dataset that consists of 14 records having these columns, namely outlook, temperature, humidity, wind, and play tennis. The target variable is the play tennis. The feature variables are outlook, temperature, humidity, and wind, which are independent and unrelated to each other. Problem: if outlook is equal to sunny, temperature is equal to hot, humidity is equal to normal, and wind is equal to weak, then what is the probability of playing tennis? To solve this problem, let us first count the number of yes and no from the 14 records of the data set. If we count how many yes, the total counted yes is 9. If we count the how many no, the total counted number of no is equal to 5. Therefore, the probability of yes is 9 out of 14, while the probability of no is 5 out of 14. Second, for every feature variable and its record values, we count the number of yes and no. Under the feature variable outlook, the sunny has 2 yes out of 9 and 3 no out of 5. If we count the number of yes under the outlook sunny, we have 1 yes, and then another yes. That makes it 2 out of 9. And if we count how many no under the outlook sunny, we count 1, 2, 3, all 3 out of 5. Similarly, if we count the number of yes under overcast, it is 4 yes out of 9 and 0 no out of 5. Under the temperature, for the hot temperature, the number of yes is 2 out of 9 and the number of no is 2 out of 5. The temperature mild has the number of yes 4 out of 9 and 2 out of 5. If we proceed to the humidity high has 3 yes out of 9 and 4 no out of 5. The humidity normal has 6 yes out of 9 and 1 no out of 5. Under the feature variable wind, the strong has 3 yes out of 9 and 3 no out of 5. And then the wind weak has 6 yes out of 9 and 2 no's out of 5. Next, we calculate the multiplication rule for independent events using this formula. The naive Bayes probability of yes is equal to the probability of yes multiplied by the probability of sunny given yes multiplied by the probability of hot given yes multiplied by the probability of normal given yes multiplied by the probability of weak given yes. We simply substitute the probability of yes to the value 9 all over 14. We substitute the probability of sunny given yes, which is 2 all over 9. We substitute the probability of hot given yes, which is 2 all over 9. We substitute the probability normal given yes, which is 6 all over 9. And then finally, we substitute the weak, probability of weak given yes, which is 6 divided by 9. The computed product of the probability of yes is equal to 0.0141093.474. Next, we calculate the multiplication rule for independent events for the naive base of the probability of no using this formula. The probability of no is equal to the probability of no multiplied by the probability of sunny given no multiplied by the probability of hot given no multiplied by the probability of normal given no multiplied by the probability of weak given no. And we simply substitute the probability of no to 5 all over 14, the probability of sunny given no, which is 3 all over 5, the probability of hot given no, which is 2 all over 5, the probability of normal given no, which is 1 all over 5, and then finally the probability of weak given no, which is 2 all over 5. We multiply and the resulting product for the probability of no is 0.0068571429. Next, we calculate the naive base probability of yes using this formula. The probability of yes is equal to the probability of yes divided by the sum of the probability of yes and the probability of no. We simply substitute the probability of yes to the value 0.014109347 and the probability of the no with this value 0.0068571429, and the quotient is 0.6729475081. And if we multiply it with 100, we come out with 67.29%. Next, we also calculate the naive base probability for the no is equal to this formula, the probability of no divided by the sum of the probability of yes and the probability of no. We substitute the probability of no with this value 0.0068571429. We substitute the probability of yes with this value 0.0141093.474, and the resulting quotient is 0.3270524919. And if we multiply it with 100, we got the amount 32.70%. To arrive into the final answer, we simply compare between the computed naive base probability of yes and no, whichever is greater. Therefore, 67.29% is greater than 32.70%. Therefore, the probability of playing tennis is yes. Example number 2. Given this dataset that consists of 8 records and has 2 columns, the first column is the email message and the second column is the label. The target variable is the label and the feature variable is the message. Problem: if you receive an email message, please buy shampoo, then what's the probability that this message is spam or ham? In the US, there is a brand of canned food named Spam, which is a ham. Here in the Philippines, we call it meatloaf. Instead of labeling not spam, we label it ham to shorten. I feel hungry. To solve this problem, let us first count the number of spam and the number of ham. But before we do so, let us first learn that the word spam is also known as junk email, and it is a unsolicited messages sent in bulk, often an advertisement to mass of people. A spam filter is a program used to detect unsolicited, unwanted, and virus-infected emails and prevent those messages from getting to a user's inbox. Like other types of filtering programs, a spam filter looks for specific criteria on which to base its judgment. Let us go back to the solution of the problem. To solve this problem, let us first count the number of spam and the number of ham. The total counted spam is 5. 1, 2, 3, 4, 5. And the total counted ham is 3. 1, 2, and 3. Therefore, the probability of spam is equal to 5 out of 8, while the probability of ham is 3 out of 8. Second, for every word from the 8 records of email messages, we count the number of spam and ham. For example, the word buy has 3 spam out of 5 and 0 ham out of 3 if we count it from the data set, if we count the word buy. Whereas the word shampoo has 2 spam out of 5 and 1 ham out of 3. The word free has 2 spams out of 5 and 1 ham out of 3, and so on and so forth. Next, we calculate the multiplication rule for independent events using this formula. The naive base, the probability of spam is equal to the probability of spam multiplied by the probability of buy given spam multiplied by the probability of shampoo given spam multiplied by the probability of free given spam multiplied by the probability take given spam multiplied by the probability done drop given spam multiplied by the probability promo given spam multiplied by the probability 1 given spam multiplied by the probability A given spam multiplied by the probability but given spam. Notice from the given that there is no word please in the dataset. That is why it is not included in this formula. Next, we simply substitute the probability of spam to 5 all over 8, the probability by given spam to 3 all over 5, the probability shampoo given spam to 2 out of 5 or 2 divided by 5, the probability free given spam to 1 minus 2 divided by 5 because the word free is not present in the given problem email message. 2 all over 5 is subtracted from 1. The probability take given spam to 1 minus 1 all over 5 because the word take is not present in the given problem email message. 1 divided by 5 is subtracted from 1 because the word take is not present in the given problem email message. The 1 all over 5 is subtracted from 1. The probability done drop given spam to 1 minus 0 divided by 5 because the word done drop is not present in the given problem email message. 0 divided by 5 is subtracted from 1. the probability promo given spam to 1 minus 2 all over 5 because the word promo is not present in the given problem email message. 2 divided by 5 is subtracted from 1. The probability 1 given spam to 1 minus 1 all over 5 because the word 1 is not present. 1 divided by 5 is subtracted from 1. The probability A given spam to 1 minus 1 divided by 5 because the word 1 is not present. The probability A given spam to 1 minus 0.5 because the word A is not present in the given email message. So 0 divided by 5 is subtracted from 1. And then finally, the probability of bot given spam to 1 minus 0 divided by 5. The word bot is not present in the email message. That's why 0 divided by 5 is subtracted from 1. The computed product is equal to 0.03456. Next, we compute the naive of the probability of harm using this formula. The probability of harm multiplied by the probability of buy given harm multiplied by the probability of shampoo given harm multiplied by the probability of free given harm multiplied by the probability of take given harm multiplied by the probability of dandruff given harm multiplied by the probability of promo given harm multiplied by the probability of 1 given harm multiplied by the probability of A given harm multiplied by the probability of bot given harm. Next, we simply substitute the probability of harm to 3 divided by 8. We substitute the probability of buy given harm to 0 divided by 3. Next, we substitute the probability of shampoo given harm, which is 1/3. Next, we substitute the probability of free given harm to 1 minus 1 divided by 3 because the word free is not present in the given email message. So 1/3 is subtracted from 1. Next, we substitute the probability of take given harm to 1 minus 2/3 because the word take is not present in the email message. So 2/3 is subtracted from 1. Next, we substitute the probability of dandruff given harm to 1 minus 1/3 because the word dandruff is not present in the given email message. So 1/3 is subtracted from 1. Next, we substitute the probability of promo given harm to 1 minus 0 divided by 3. The word promo is not present in the email message. That's why 0 divided by 3 is subtracted from 1. Next, we substitute the probability of 1 given harm to 1 minus 0 divided by 3. The word 1 is not present in the given email message. That's why 0 divided by 3 is subtracted from 1. Next, we substitute the probability of A given harm to 1 minus 1 divided by 3 because the word A is not present in the given email message. That's why 1/3 is subtracted from 1. Finally, the probability of bot given harm is substituted to 1 minus 1/3 because the word bot is not present in the email message. Therefore, 1/3 is subtracted from 1. Notice that the word please is not present in the data set. That's why we will not include to the formula. The computed product is 0. The probability of harm is equal to 0. Next, we calculate the naive Bayes probability of spam using this formula. The probability of spam is equal to the probability of spam divided by the sum of the probability of spam and the probability of harm. The probability of spam will be substituted to 0.03456. The probability harm will be substituted to 0, and the quotient is 1. If we multiply it with 100, it is 100%. Next, we also calculate the naive Bayes probability of harm using this formula. The probability of harm divided by the sum of the probability of spam and the probability of harm. We substitute the probability of harm to 0. We substitute the probability of spam to 0.03456. The quotient is 0, and if we multiply it with 100, therefore it is 100%. To arrive into the final answer, we simply compare between the computed naive Bayes probability of spam and harm, whichever is greater. Therefore, 100% is greater than 0. We can conclude that the probability is a spam. The email message, "Please buy shampoo," is a spam. In the field of machine learning, and specifically the problem of statistical classification, a confusion matrix, also known as an error matrix, is a specific table layout that allows visualization of the performance of an algorithm, typically a supervised learning. In unsupervised learning, it is usually called a matching matrix. Each row of the matrix represents the instances in an actual class, while each column represents the instances in a predicted class, or vice versa. Both variants are found in the literature. The name stems from the fact that it makes it easy to see whether the system is confusing two classes, for example, commonly mislabeling one label to another. To understand better a confusion matrix, let us take a look at this table. Suppose there are 12 records in the data set. The actual classification is the real data collected, while the predicted classification is the prediction of the trained model, such as the naive Bayes, neural network, and so on. At column 1, the actual classification is 1, but the predicted classification is 0, therefore it is false negative. Our trained model is bad. At column number 3, the actual classification is 1, and the predicted classification is also 1. Therefore, it is true positive. Our trained model is very good. At column number 9, the actual classification is 0, but the predicted classification is 1. Therefore, it is false positive. Our trained model is bad. At column number 10, the actual classification is 0, and also the predicted classification is 0. Therefore, it is true negative. Our trained model is very good. In the confusion matrix diagram, the ideal sum of both true positive and true negative must be 100%, while the ideal sum of the false negative plus the false positive plus the false negative must be 0. This is the code of the spam filter using the naive-based classification algorithm. It is written in the Python programming language. This program uses the NumPy, Pandas, sklearn, matplotlib, and Seaborn libraries. The line 25 load the spam filter data set. The file spam.csv. This is the contents of the file spam.csv, a comma-separated value file format file. It has 5,572 records of email messages. At line number 29, it will display the total records of email messages. At line number 32, it will count the number of spam and the number of ham. And it will also display the count. At line number 38, it will map the labels ham to 0 and spam to 1. At line number 42, it will drop the column category because we added a label from line number 32. It will transform that word ham to 0 and spam to 1. At line number 46 and 47, it will assign the variable x to message and variable y to the label. At line number 53, 54, it will split the dataset into two. One is the training dataset, which is 80% of the 5,572 records of email messages, and the test dataset to 20% of that 5,572 records of email messages. At line number 64, 65, 66, it will vectorize the messages or the sentences, and it will remove stop words. Stop words usually refers to the most common words in the English language. Stop words are the words in any language which does not add much meaning to a sentence. They can safely be ignored without sacrificing the meaning of the sentence. For some search engines, these are some of the most common short function words, such as the word the, is, at, which, and on. At line number 71, it will display the vocabulary size. At line number 74 and 75, it will transform the train and test data set into a sparse matrix. At line number 83 and 84, it will build a naive Bayes model using the multinomial classifier, which counts the frequency of words. At line number 89, it will train the naive Bayes model. At line number 97, it will predict the class. At line number 100, it will predict the probabilities. At line number 104 and 105, it will display the accuracy that we evaluate the naive Bayes multinomial classifier model. At line number 108, 109, it will determine the confusion matrix, the true negative, the false negative, the false positive, the true positive. At line number, beginning at line number 134 until line 147, it will display the confusion matrix diagram. And then finally, the while loop statement will accept input from the user and then predict if that input message is a spam or ham. Let us run and test. The evaluation of the naive Bayes model, the accuracy score is 99.01%, which is very good. Now we look at the confusion matrix. The true negative has 86.55%. The true positive has 12.47%. If we add the sum of the true negative and then the true positive, it is around 99, more than 99%, which is very good. But the ideal is 100%. If we look at the false positive, it is 0.27%. If we look at the false negative, it is 0.72. If we add the false positive and then the false negative, it is around 0.99%, which is near to 0, which is very good. But the ideal is 0%. Now let us enter some email message and then determine what is the prediction of our naive Bayes model classifier. The message is a ham. Since I made a mistake in the typographic error, let us input again that message. You won raffle promo. Now the prediction is spam, which is correct. Do you want to input another message? Yes. The email message is a spam. Do you want to input another message? Yes. The email message is a ham. Do you want to input another message? No. That ends our topic for today. I hope you are inspired in my class. Thank you for watching. God bless us.